Alright, so the focus of this video is going to be differentiating ln x with respect to x. Now again, on page 25 in your log tables, you will see that we are told that ln x goes to 1 all over x. Now, we won't always have a question where we just have x here, so let's take a look at some examples where it's not going to be ln x. Let's take a look at an example where it is ln of 2x. And let's examine more closely what happens. So when we apply these rules, we have to remember that there's actually a function within a function here. Well, what do I mean by that? So it's a composite function, and it means that if you are to put in an input, for example, x, and you put that in, the first thing that's going to happen to it is you're going to double it. So you're going to multiply that by 2. So we're going to multiply by 2, and what happens is out of this function machine comes 2x. Now, when we get that answer, what happens is we feed that into another function machine, and we're going to get ln of that answer. So whatever that answer works out to be out of this function machine, you feed it in here, and you get a second one. So it's a function inside a function. So we need to pay particular attention to that. So when we're using this, we're actually going to be applying the chain rule to get our answer. Now, the chain rule, to fully appreciate that, you would need to have a look at U substitution. Now again, if you're not comfortable with U substitution, that's okay, but try and understand that it's a composite function and we need to differentiate not only the ln x, but the 2x involved here. So let's have a look. So we said that the log tables tells us that 2x, that 2x goes to, or the ln x becomes 1 all over 2x. That was our x there. So looking at the previous example, the x goes to 1 all over x. In this case, our x is the 2x, so he goes there. Now that was us differentiating ln. ln goes to 1 all over x. But we have not paid attention to or dealt with the 2x yet. So remember, there's two functions. We've done this function, the ln. We have not done the 2x as of yet. So if we were to differentiate 2x now, we would know that 2x goes to 2. And if you're uncomfortable with that, go back and have a look at the earlier videos. But 2x goes to 2. So our final answer will become 1 all over 2x by 2. Which is the same thing as saying 2 all over 2x, which we can simplify down to 1 all over x, because you've got 2 multiplied in on the top and 2 multiplied in on the bottom, so you're multiplying and then dividing, so they become 1. And that's what we get there. So remember, whenever you're dealing with ln, e to the x, cos x, sin x, tan x, the inverse rules, you're always thinking about two functions. And if you're talking about two functions, you need to address both of them. So let's take a look at another example. So let's look at y is equal to ln of x squared. So what we will get here is that dy dx of ln, first of all, we can do all of that. ln goes to 1 all over x squared in this case. So 1 all over x squared. So you bring your x, in this case it's x squared, and you bring it to 1 all over x squared. Now that was us differentiating the ln part of that function, or that composite function. We need to remember that there's actually two functions there. In this function machine, what you're doing is you're going to be putting in x into that function machine. You're going to square your input, and you get out x squared, and then that gets fed into another machine, a second function, that is saying get ln of the input. So you get ln of x squared. So remember that it's a composite function. There's two things going on. You're squaring it and then getting ln of it. So while we have differentiated the ln, we have not yet differentiated the x squared. So we then multiply by the 2x. And again, if you want to know how that works, please look at the U substitution video. Multiplying this out, then we get 2x all over x squared. We can say that that is the same thing as 2x all over x by x. Why am I doing that then? Well, I can see that x is multiplied in on the top and multiplied in on the bottom, which means divide. So multiply and divide by x, well, that becomes 1. So our final answer here is 2 all over x. One more example of this. Let's have a look at, for example, y is equal to ln of cos x. So let's take a look at this guy. So we know then dy dx goes to, for dy dx of ln, it goes to 1 all over x. In this case, our x is cos x, multiply by the differential of what is in the bracket. Because remember, composite function, this is a function, this is a function. We've dealt with the ln, we have not dealt with the cos x. Now we know from the log tables, page 25, cos x goes to minus sin x. And we would have to, again, be extremely careful there. If that was a cos 2x, it would change things up. Let's just quickly take a look at that. If it was cos 2x, we'd have to be careful there as well. So ln of, we're saying cos 2x. So again, we go dy dx, and ln, again, when we differentiate ln, it goes to 1 all over cos 2x. And then we must remember, well, we've dealt with the ln part of the composite function. We have not dealt with the cos 2x. So what we are going to do there is turn cos 2x into minus sin 2x. But cos 2x is a function, a composite function itself. And we must remember that while we have differentiated the cos, we have not dealt with the 2x here. So we must multiply that itself by 2. And if you're unsure about what I've done there, check out the trigonometry or trigonometric differentiation video. So multiplying that out, then we get minus 2 sine 2x all over cos 2x. Which you can tidy up further, but we're going to discuss that when we do trig identities. Okay.